We are now ready for problem 10 of these review problems. The first video was the first 9 problems, and they all dealt with if we were given a graph, how do you determine the limit of the function if you're given the function as a graph? However, now we're going to start working on determining the limits of functions when the function is given as an equation or an expression. Let me go ahead and just show you the first problem we're going to work on, and I'm going to go ahead and write a little bit. So you notice here's problem number 10. Says the limit as x approaches 3 of 7x plus 9. I'm going to write that down, and then I'm going to talk a little bit and just do a quick review of how we solve these kinds of problems. All right, so here, let me go back to my paper now. And we'll just do a quick review. If you watched any of my videos that I made about limits, I don't think limits are too hard. Here's what you do. When you're trying to find the limit of an expression like this, the first step is you plug in the number for x and you see what happens. And actually, there's only 3 possibilities. So the first possibility is it equals a number. When you plug in the number for x in the expression, now when I do this problem in a minute, well, I guess I can do it right now. You plug in 3 for x, and you get 7 times 3 plus 9, 21 plus 9 equals 30. It just equals a number. In that case, you're done. In a minute, I'm going to enter this as the answer, and I hope it should be correct. So you plug in the number for x, the expression equals a number, you're done. There'll be some problems, and I assume we're going to do some in a few minutes, where you plug in the number for x, and then you get something that's undefined. Usually, oftentimes, you might end up with a 0 in the denominator of a fraction, which of course we can't have in math, so we just stop and say it's undefined. Or maybe you end up with like a negative number under a square root. So there are those couple of cases where in the world of math, we stop because it's undefined. So if that happens, then your answer is simply, that's the answer for no solution. It's undefined. Now there's only one more thing that can happen, right? So we've plugged the number in for x. You do the math. If you get a number, you're done. If you get something that's undefined, you're also done, and there's no solution. But occasionally, and this only happens if your expression is a fraction, sometimes you end up with 0 over 0. I mean, this is really a pretty special case. So what do you do when you have a case where you have 0 over 0? You actually, you try and factor the top and the bottom of the fraction. And then you see if some stuff cancels out. Usually the problems are going to give us, this happens. Some stuff cancels out of the top and the bottom. And then you try again. By try again, I mean, after you've canceled out, you plug the number in for X and then see if you get an answer. So that's it. When you're trying to take the limit of an expression like this, you plug in the number for X. These are your three possibilities, and then you're good to go. So let's go back now. This first problem I did here, and I'm saying it equals 30. So let's go ahead and see if I'm correct. So I'm trying to find, here it is. So I said, I believe this answer is 30. I check my answer, lo and behold, it is. Let's see the next one. All right, the limit as x approaches -5 of x squared minus 9. Now I can sort of do this in my head because I think it's simple enough. So you plug in -5 for x. Well, let me go and show it. Matter of fact, how about I do this? Let me write down the next 3 or 4 problems, and then I'll do them all, and then I'll come back and plug them in and see if I did them correct. So this is number 11. So this is the limit as x approaches -5 of x squared minus 9. I'm going to skip to the next problem. So number 12 is the limit as x approaches -8 of x squared minus 1 over 8 minus x. So I'm writing these down, and in a minute, I'm going to switch to what I've written down and work all these out and see what the answers are. Let's just do a few more. So number 13. The limit as x approaches 6 of x squared plus 3x minus 54 over x squared minus 36. Now in a few minutes when I do these problems, I'm going to have to factor. Hopefully all of you remember how to factor these polynomials. Okay, look at problem 14. This one's different because look at my limit as x approaches infinity. When you have these expressions, when x approaches infinity, the method to solve this one is totally different than the previous problems. The previous problems was the limit as x approaches a number. The method I just showed you is what you do when x approaches a number. In a few minutes, we'll come back and talk about this because the limit as x approaches infinity is a totally different method to solve this kind of problem. So I'm going to go back to problem 11, and I'm going to switch now and work out these 3 problems. So number 11 was the first one. The limit as x approaches -5 of x squared minus 9. So what do? You plug in -5 in for x. -5 squared is 25. Please don't put negative 25. Sometimes I'll see students do that. X squared, negative 5 times negative 5 is 25 minus 9 equals 16. So what happened? I plugged in the number for X. It ended up being a number. That should be my answer. So let's do this. I'm not going to check it yet. We'll check them all at the same time. So 11, I'm saying the answer is 16. 12, got a fraction here, but the first step is always plug in the number for X. So X is approaching negative 8. So negative 8 squared minus 1 over 8 minus a negative 8. So be careful of your math, especially now that I got these subtractions and minuses here. Negative 8 squared is 64 minus 1. 8 subtracting a negative 8. When you subtract a negative number, it's like adding. So it's really 8 plus 8, which is 16. So I really end up with a fraction 63 over 16. And you always need to see if you can reduce the fraction, but it does not reduce. Sort of an ugly answer, but that's what I have. Whoops. I've already written down 13 on this next page. First thing you do is plug in 6 for X and see what happens. 6 squared plus 3 times 6 minus 54 over 6 squared minus 36. So if I'm careful with my math and order of operations, 6 squared is 36 plus 18 minus 54 over 6 squared minus 36. 36 minus 36. So you add 36 and 18, which equals 54. Subtract 54, you get 0 on top. 36 minus 6, 0 on the bottom. As a matter of fact, when we go back and look at this problem, they pretty much in the instructions told you you were going to get 0 over 0. I don't know why they did that. You can easily figure it out on your own. But here's the case where you end up with 0 over 0. So what do? You go back to the original expression and you look at the top and see if you can factor it, and look at the bottom and see if you can factor it. And if you can factor them, then hopefully some things cancel out and then we try it again. So here's what I'm going to do just to be thorough. Let me rewrite this whole problem. Now the denominator, it's pretty easy to factor if you remember difference of squares, right? Should be x plus 6 times x minus 6. The numerator at the top is a trinomial. I typically use the method we teach called product sum, where trying to figure out two numbers I can multiply together that equals negative 54. But when I add them, it equals 3. And just because I've done this enough, I believe it should be x plus 9 times x minus 6. Because 9 times 6 is negative 54, but then 9 plus a negative 6 is 3. So this is, I've now factored this. And I notice I have identical parentheses as factors in the top and the bottom. I can actually cancel out the whole parenthesis. And now I'm left with the limit as x approaches 6 of x plus 9 over x plus 6. So now that I've factored and I've canceled, you try it again. And by trying again, that means now you plug in your number for X, and now you see what happens. So 6 plus 9 over 6 plus 6. So that's 15 over 12, which actually this reduces into 5 over 4. All right. Now let me just for fun, you didn't have a problem. What if I had the limit of x approaches 6, x squared minus 36. So I had this problem. I would go ahead, plug in 6 for x and see what happens. Four over 0. What happens when you try and divide by 0? A number by 0. It's undefined, therefore there's no solution. So this is the third thing that can happen. I don't think there are any problems like that in the review, but just want to remind you of that. All right, I'm going to go back and plug in my answers and see, and cross my fingers and hope I did not mess anything up. So I said the answer for number 11 is 16. That's good. And then I said number 12 is 63 over 16. Now you learn in my math lab, sometimes you can do shortcuts, like instead of having to click on the fraction down here, if it's just two numbers, I think you can just put 63/16 and not have to point and click. And actually it's correct, so that's good. Then the last one, when we worked out problem 13, ended up being, so you look at problem 13. The initial substitution of x equals a, that's saying when you plug in the number for x, gives you 0 over 0. And they almost tell you what to do. I mean, they don't really need to tell you this. You guys are plenty smart. When you plugged in 6 for x, you would have found out you had 0 over 0. But anyways, they told you. And so therefore, when we did the problem, we ended up with 5 over 4. So once again, 5 divided by 4. Cross our fingers, and it looks correct. So now let me do this. I'm going to write down, I assume we have a few problems where we have the limits as x approaches infinity. Let me just go and write these problems down, and we'll do them, and I'll quickly review the method I use to solve these problems. So 14 looks like a pretty nasty expression. The limit as x approaches infinity of 24x cubed plus 4x squared minus 3x over 32x cubed plus x squared plus 5x plus 5. I'm trying to make sure I don't copy it down quickly. Let me just go ahead, because I assume there could probably be a couple problems just like this. Yeah, look at number 15. Same kind of thing. The limit as x approaches infinity of x squared plus 15 over x cubed plus 6. See if there's another one. Nope. I guess there were just two of them. All right. So let's go back to the first one. Then we're going to go to the paper. And we'll work out these two problems where we're looking at the limit as it approaches infinity. Now, once again, if you watch the videos I made, the YouTube videos, I gave the whole reason and how to solve these problems. So I'm not going to really explain why I'm doing what I'm doing. I'm just going to do it. But if you watch them, the way I like to do it is you take the top and the bottom and you reduce it to the leading term. So you get rid of all this stuff. And once again, if you're not quite sure why I'm doing this, then feel free to go back and watch the videos where I explained all this and did examples. So once you do that, you end up with 24x cubed over 32x cubed. X cubes cancel out. So really, at this point, you didn't even have any variables left. So it's obvious that the limit is just going to be 24 over 32, which reduces down to 3/4. So in this case, as x approaches infinity, the limit of all this is 3/4. We'll plug that in a minute and see if that's a correct answer. Do the same thing here. Get rid of everything but the leading terms. So you're left with the limit as x approaches infinity of x squared over x cubed. If you cancel and reduce these, have the limit as x approaches infinity of 1 over x. Here's what you do. So if you plug in for x infinity, you can think of the infinity as a very, 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 very large number, like 1 billion or 100 billion or some huge number. What does this approach? As x gets huge, what does this approach? What is 1 over a huge number? Basically approaches 0. So that should be the limit for number 15. So let me plug those in. Let's see if we're correct. And once again, if you want to understand this and see some examples and explain everything I've done, you can go back and watch my YouTube videos where I really take my time and explain and do lots of examples. So for 14, I'm saying the answer is 3/4. Oh, is my computer slow? Yeah, okay. I was getting worried. And then for this one, we said it's 0. All right, that's a little better. That was quick. So now what do we have next? Whoops. All right, here we go, 16. All right, now we have some problems on seeing if functions are continuous. Once again, I've created YouTube videos where I explain what continuity is, how to check for it, how to check continuity for a graph, how to check it for an expression. So I'm not going to go over it now. I will do the problems, but I won't explain exactly why I'm doing what I'm doing. Now for this one, they're asking determine whether the function shown is continuous over the interval -6 to 6. So we're talking about values of x here. So it's saying, okay, between x equals -6 and x equals 6, is this a continuous function? So continuous function means there's no breaks, gaps, or jumps. If you watch the video, when you're drawing a graph, the idea is, can you trace out the function and never have your pen or pencil leave the paper? If you can, then we say it's continuous. So -6 is here. So if you imagine myself redrawing this, can I redraw this whole function? I'm going to go from -6 to 6. can I redraw this whole function and never lift my pen or pencil up off the ground? Even though there's a sharp corner here, I can still keep drawing and keep drawing. And what have I done? I've been able to trace out the whole graph from -6 to 6 without ever lifting my pen. When you can do that, that means it's continuous. (17). Another one, determine whether the function is continuous or the interval -6 to 6. Let's look at this graph. Same idea, we start here. I'm tracing out the function. I want to go from -6 to 6. I get to here, and here this part ends, and I jump down to here, and then keep on going. But the way you check for continuity of a graph is, can you draw the whole graph without ever lifting my pen or pencil off the page? And obviously, I can draw the graph up to here, but then I have to jump down and keep going here. Well, there's a big gap there. And there's no pen or pencil marks, so the only way I can get from here to here is to lift my pen or pencil off the page. And therefore, I say it's not continuous. There's a break and there's a gap here. So I would say no, it's not continuous. Now here, we're back to limits. This is a limit problem. Looks like, actually, the first three parts, A, B, and C, are checking limits. It looks like part A, as x approaches 2 from the negative or the left side. Part B, the limit as x approaches 2 from the positive or the high side. And then the limit as x approaches 2. So what this is doing, remember I said the way you find a limit when x approaches a number is you get the limit from the left and you get the limit from the right, and if they're the same thing, then you have a limit. That's what we're doing here. They're sort of doing the steps for us. So we'll see what happens, and then look at the very end what they have, and we'll discuss this when we get to it. So here's the graph. First thing we're going to look at is we're looking at the limit of the function as x approaches 2 from the negative side. So here's x approaching 2. So from the negative side, what's the function approaching? It's approaching 3. So I'm going to put a 3 in here. Hopefully it's correct. All right. Then the next one says, hey, look at the limit as x approaches 2 from the positive side. So now I come from the right. I'm approaching x equals 2. And as I'm approaching x equals 2, what's the function approaching? Looks like the function is approaching 2. So I put a 2 in here. And I check it. And it's correct. So now they say, okay, so now what's the limit as x approaches 2 of the function? Well, I just said it a minute ago. The way you find the limit of a function is you take the limit from the left, you take the limit from the right. If they equal the same thing, then you have a limit. Well, we've already done those steps. The limit from the left was 3 as x approaches 2. The limit from the right as x approaches 2 is 2. Since those are not the same, there is no limit as x approaches 2. Because for there to be a limit, the limit from the left and the limit from the right have to be the same thing. So for part C, I'm going to say there is no limit, and that is correct. Now the last part is interesting. Don't be fooled now, because we've been doing limits left and right, but this is just basic old function notation. This is saying what's the value of the function when x is 2, right? F of 2 means f of x. F of 2 says, all right, let's go see what happens, see what the function is when x equals 2. So x equals 2 is right here. Here's my function. Of course, x equals 2 is where we have this gap or this break or this jump. So the question is, what's the function? Is it 3 or is it 2? Well, the whole key is, when you have the circle filled in, that means to include that point or that value. And if you have an empty circle, that means you don't include it. So when x is 2, it's saying actually this is the value of the function at the top here and not here at the bottom. So basically f of 2 we would say is 3. All right, so that's good. Now this is similar, but let's look at the questions, then we'll talk about it for just a minute. They're going to have us find the limit of the function as x approaches 4 from the right and from the left, because we've done that before. Then they're asking, based upon what we just found out in A, we can answer the question in B, what's the limit as x approaches 4? And then, just like we've done a minute ago, now they go say, okay, find the value of the function when x actually equals 4. But now they add a fourth question. Is f of x continuous at x equals 4? Why or why not? Now, once again, I made the YouTube videos on checking for continuous functions, but what has to happen is it's really a 3-step process. Like in this case, really, essentially what they're doing is they're checking to see if the function is continuous at x equals 4. Let me explain the theory, and then we will look at the graph, and you'll see where it should all make sense. Theoretically, the way you check for continuity mathematically is you determine the limit of the function at that point. You determine the actual value of the function at that point. And if those two things are the same, then you say it's continuous. So basically, you're comparing the value when x approaches a number, and then you're checking the actual number itself. Now, we can look at this graph, and from what we know, look at this. Graphs, it's easy to check continuity for graphs, right? We're coming along here, and what happens? We have this big gap, this big jump. We have to lift our pen off the page to trace this thing out. So we can tell you right now, at x equals 4, this is not continuous. But let's answer all the questions. So the first question says, look at the function. What's the limit as x approaches 4 from the positive or the right side? So here's 4. As x approaches 4 from the right, it looks like, what is this? 1, 2, 3, 4, 5, 6, 7. So let's try and keep that in our mind. Oh, we'll have to keep it in our mind. That's the answer. 7. And next, it wants to know the limit as x approaches 4 from the negative or from the left. So here we come in from the left. What's the function approaching? Looks like 2. Now, they say, what's the limit of the function when x approaches 4? Of course, we've already done the work because in part A, we looked at the limit as x approaches 4 from the high side or the positive side, and the next part was from the low side. There's only a limit if those two things are equal. Since those numbers are different, as it turns out, the limit does not exist. Now the next question is, they say, okay, so what is the value of the function when x is 4? So if you look at our graph again, so when x is 4, once again, the open dot means the function does not exist there. The closed dot means where the function exists. So it looks like it's 1, 2, 3, 4, 5, 6, 7. Looks like the function equals 7 when x is 4. Is there any more question? Oh yeah, here it is. So based upon everything we've learned so far, is f of x continuous at x equals 4? It's definitely not continuous. You can look at the graph, but now we have to give, it's funny how we know it's not continuous, but there are two possible answers of no. So we have to look at the reasoning. So B says no, fx not continuous at x equals 4 because the limit as x equals 4 does not exist. That's true. The limit doesn't exist. There is no limit. C is also no, f of x is not continuous x 4 because f of x is undefined. Well, that's not true. F of 4 is defined. It has an answer. Matter of fact, we gave it. So that means B is actually looks like it's probably the correct answer. All right, let's see what we have next. All right. So let's go and do this because now we're checking continuity of a function, but we don't have the graph. All we have is the function. So I'm going to go and write this down. We're looking f of x, this is number 20. F of x equals 3x minus 2. And they're asking, is this function continuous at x equals 2? And once again, it's interesting, 2 no answers, 2 yes answers. So once you figure out if it's no or yes, then you have to look at the reasoning why and pick out the correct one. So let me work this out. So here's problem 20. Here's the function. And we're looking at when x is 2, is this function continuous? So once again, it's a 3-step process. The first step is go ahead and see what the value of the function is at x equals 2. So whatever value of x you're looking at, simply plug it in for x. 6 minus 2. So f of 2 is 4. The second thing you do is you take the limit as x approaches 2 of the function. So part 1, since we're interested when x is 2, part 1, you plug in 2 for x. So f of 2 is this. The second part is you take the limit as x approaches 2, right? Now, how do you let me go and write this. So what this is really saying is, what's the limit as x approaches 2 of 3x minus 2? Well, we know how to do limits like this, right? The first step is you plug in the number for x and see what happens. If I plug in 2 for x, 3 times 2 minus 2 is 6, minus 2 is 4. So now you've done the first step and the second step. The third step is pretty simple. Are the answers from the first step and is the answer from the second step the same? If they are, then it's continuous. If the answer is no, not continuous. So for our problem, they're the same. So yes, the function is continuous at x equals 2. Now let's go see what the actual answers are, because there are 2 yes answers. And let's see if we figure out which one is the correct one. So B and C are both yes. B says yes, f of x is continuous at 2 because the limit of f of x as x approaches 2 is equal to the function 2. That's true. This, in a sense, is saying the test we did to check for continuity. Let's just see what C says. Yes, f of x is continuous at x equals 2 because f of 2 exists. That's not enough. The actual way you find out a limit, or the way you find out if it's continuous, is stated right here. So it's definitely B. All right, let's keep on going. Let's finish off these continuity problems. This one's a little trickier because now the function's a piecewise function, right? Piecewise function means it's like 2 different functions smushed up next to each other. Looks like the transition for these 2 functions is when x is 3. So that's where the function changes. And not surprisingly, their question is the function continuous at x equals 3? Well, the same principle applies. It's the same 3 steps. Remember, the first step is go see what the function is equal to when x is equal to 3. And the second step is find the limit of the function when x equals 3. Then the third step is you look at the answers of the first 2 steps and see if they're the same. So let's just go and do this. This can be a little confusing. I'm going to write this down and we'll work it out, and I'll talk about it as I work it out. So g of x, piecewise function. The first part is 1/3 x plus 4 when x is less than or equal to 3. And then the second function is 3x minus 2 for x greater than 3. And they're asking us, is it continuous at x equals 3? Now, they didn't give us the graph. I think earlier in our problem, just for fun, if they give you a graph, I mean, here's like, I'm not going to draw this perfectly, but say here's the first function, and say here's the second function. Would it be continuous at x equals 3? No, there's a gap there. How about here's the first function, and then here's the second function. Would this be continuous? Yes, because there's no gap or break, even between the 2 functions. So you know what we're going to do? We're going to first check. I don't know which one of these it's going to be, but we're going to go see what the value of the function is at that value of x. And then we're going to take the limit as x approaches 3 of the function. And then we ask the question, are those two equal? So the first part, what is the function when x is 3? Well, the key is I have to figure out, since I have two functions here, I have to figure out which one applies. So I get to see which function do I use when x is 3. Now, x3 is the boundary point, but I notice this first function has x less than or equal to 3. So this first function is the one that includes when x is equal to 3. So basically, I plug in 3 for x of my first function. 1/3 times 3 plus 4. 1/3 times 3 is 1 plus 4. So it looks like f of 3 is 5. Now here's where it gets a little tricky. The next thing I have to do is look at the limit as x approaches 3 of the function. Now you remember, how do we figure out the limit of a function? Well, we start from the left and we approach the value of x and see what the function is equal to, and then we go at it from the right. So from the left, so in a sense, here's what we do. Whoops. This is like approaching it from the left, right? The limit as x approaches 3 from the left of f of x. Well, when x is less than 3, this is the function we use. So to find the limit, I simply plug in 3 into here. And I get 3 times 1/3, which is 1, which is 5. Now that's coming from the left. I also have to see what happens when I come from the right. Because once again, I have to do these two parts to see the limit when x is 3. I have to come from the left and come from the right. Now, when I come from the right, that means x is larger than 3, and I have to use the second function. And to find the limit, I simply plug in x into this function. So I plug in x, 3 for x. 3 times 3 is 9, minus 2 is 7. Now, for the limit, for this limit to exist, these two need to be the same. Since they're not the same, the limit does not exist. Now, to check continuity, why we're doing this whole problem is we're checking to see if part 1 and part 2 are equal. Well, part 1 is 5, part 2 is undefined, therefore they're not equal. And we're going to say this is not continuous at x equals 3. So I'm going to, is the function continuous? I'm going to say no. And thankfully it's correct. All right. So that's actually the last question on continuity. So now would be a good time to stop. And we will continue on with number 22 on the next video.